right, so as I mentioned, Chapter 11 is AC power analysis, right? So we're going to talk about, as I mentioned, several different types of power or versions that we're going to look at. We're going to start out talking about instantaneous and average power. We'll talk about, we've talked a little before about power transfer when we did Thevenin equivalence. We'll talk some about maximum average power transfer, so how that equates into AC circuits. We're going to introduce a really important concept when dealing with AC power and AC circuits in general called RMS, the root mean square value. Then we'll talk about, again, all these flavors of power: apparent power, the power factor, the complex power, right? And then how we do conservation of power for AC, which we saw for DC, power factor correction, and power measurement. Power factor correction is a great topic for anybody who's interested in utility work. So if you're thinking about going to work in the electric industry, like for United Illuminating or Connecticut Light and Power or any of the other electric providers, power factor correction is a really big deal. So let's start out with the idea of instantaneous power. This one probably makes the most sense in terms of what we have seen before, because it's just what we know power to be, which is voltage times current. So power is VI, right? Except that right now we're dealing with a voltage and a current that are varying in time. So just put those expressions in and multiply the two of them together. And at any given point in time, you can find out what power is being dissipated in your circuit at that moment in time, right? When we put the two sinusoids together, right, so we have a cosine omega t with the phase shift of the voltage, cosine omega t, here's the phase shift for the current, right? We have two cosines multiplying each other. There's a trigonometric identity that allows you to put them into this form. And you'll notice that there's this constant power term that, because the cosine of theta v minus theta I, that's just a number, right? Just a constant. So there's this piece that doesn't change, and that's basically that, right? Where that's coming from is this offset in the voltage and current. If you were to plot this power, right, you'll see that there's this constant level that it's oscillating around. That's the constant power. However, then there's the sinusoidal power. And because we've multiplied two different sinusoids together, the sinusoidal power comes out at twice the original frequency. This is the trig identity, right, that they're using. So you get this quickly varying piece. So you may, at any moment in time, be far below your constant power level, right? But if you were to think about as constant power, you can kind of think about that as sort of the average value, right, of the power throughout time. It's also important to remember, just like before with DC, when power is greater than 0, we're saying that is the power being absorbed by the circuit. This is the rule we used when we developed the passive sign convention at the beginning of circuits, where all passive elements should have a positive power, meaning that the current should flow into the positive terminal of the device, and that yields a positive power number. Positive current times a positive voltage, positive power. Power is being absorbed or dissipated by that element. So resistors get hot, right? If the power is less than 0, that means that the power is being absorbed by the source, right? And so like you're charging a battery, right? Something like that. Or, resistors can't provide power, so they shouldn't have a negative power. That's why, again, that passive sign convention rule came in, where we said if you had that happen, that a resistor had a negative power, that just means the voltage or current has a minus sign on it. And we put that in manually. Okay? So the average power is just the average of this instantaneous power across one period. So now we start to look at this idea that, again, sinusoids are periodic functions, so we're always going to deal with, usually, going to deal with one period of the function. And so we take the average by doing an integral and dividing by the period, right? So the integral adds up all the power, and then the period divides by the bottom, and you get the average value. And it really is this constant value, right? And so that first piece is a good number to keep in mind. the average power is not time dependent. Okay? There is no t in this leftover expression, right? Also, you can note that when the phase shift of the voltage equals the phase shift of the current, right, we get cos of 0, which is 1, right? Which means we have a purely resistive load. Our impedance is a resistor. There's no effective capacitance or inductance in the circuit, right? Because remember when we saw the phase relationships for the three elements, we had a table that looked like, I think it was an inductor. We had a table that looked like this, and there was a complex plane under each one of them, and we showed that the resistor has the voltage and the current at the same angle, right? And that there was a 90-degree phase shift between inductors and capacitors. So resistors have no phase difference between voltage and current. And so this whole term right here becomes 1/2 Vm Im. It just becomes that constant value right there. If, however, the theta V minus theta I is 90 degrees, right, plus or minus, then that means it's a purely reactive load. Because 90 degrees is I, right? That's, or J, that's the imaginary number, a phase of 90 degrees. So that tells you you have a pure inductor or capacitor. No resistance, no effective resistance, right? Also, if there's 0, if somehow this turns out to be a 0, which could be the case if there's a 90-degree phase shift, right? Because cosine of 90 is 0. That means you absorb no average power. So, if you think back in chapter 8, I had mentioned a little circuit that was an LC circuit like this, right? And we called this a tank circuit. And when we calculated the time response of this tank circuit, it was a pure, non-decaying sinusoid for all time. We said because there was no resistor in there to absorb the power, right? So power sloshes like a tank of water back and forth. The energy gets stored in the inductor, and then it moves over here to the capacitor, and then it moves back over here to the inductor, back to the capacitor, and never goes anywhere else. We don't ever lose any of it. Yeah?
T equals 0, does that mean all the power is going to the source, or it means it's all dissipated?
It means there's no dissipation at all.
Okay.
And no new power would necessarily be drawn from the source either, right? Because whatever power you've got, it's all power moving, all of the energy is moving back and forth. Net change, there's no net change in energy, meaning there's no power that's there's no power. So whatever energy is already stored in the circuit just moves back and forth, right? So that doesn't mean you don't see the sinusoid. Just because average power is 0, that just means that this constant line is down here. So it oscillates up, but for every time it oscillates up, it goes back down. And it cancels each other out, right? Because if you were to take a standard sinusoid and take an integral of it, you get 0, right? Because if I average this out, for every piece that's up, I have a piece that's down. And they cancel each other out. So that's what the average of equal to 0 means. So, but those are a couple of good things to keep in mind. Again, we have to start tracking all these different labels we put on the power. And average power is good because it's a good one to remember, because average power relates to the real power in the circuit. Like that means that's power we're actually paying for from the utility company, right? So how do we calculate it? Again, these are relatively straightforward because this one is just VI, right? So if I want to know the instantaneous power, right, and the average power absorbed by this passive linear network, I can just look at these guys. I'm going to plug them into my formula right here. Just multiply the two of them together, right? I don't want to have to go through the whole trig derivation though, so I'm just going to remember, okay, I need to look at what my amplitude of my voltage and my current are, and I need to look at what the phase difference between them is. On this oscillating term, notice that it's the sum of the phases. Right? Okay. So if I look at this, okay, I've identified Vm equals 80, Im equals 15, right? Theta sub V is 20, and theta sub I is 60. So just put those together, and I can find the instantaneous power by writing down the full expression. So little p of t, right? 1/2 Vm Im, so 80 times 15, times the cosine of the phase difference between the voltage and the current, right? So this is 20 minus 60, which is going to be negative 40 degrees. Let me double check I wrote those in the right order. Yes, voltage minus current. Okay. Oh, sorry. Then the second piece, so that's the average power, right? Not time varying. Then to add on the time varying piece, the same 1/2 Vm times Im, cosine of 2 omega t. Omega is 10, so this is 20t, plus the sum of the phases. 60 plus 20 is 80. And so here's the average power. This whole thing is the instantaneous power, right? So that's the sinusoidally varying part, but the instantaneous power, you need the whole expression, okay? And then again, on your calculator, just plug these in and calculate the number. It's worked out for us down here. So the average power component is 385.7, and the sinusoidally varying part, just the coefficient together, it's the 600. What? Oh, whew. Where'd that minus 10 come from? Ah, I wasn't paying close enough attention. This is not a cosine times a cosine. This is a cosine times a sine, right? Yes. So, I don't have 80, right? I have to subtract 90 degrees from my phase to turn the sine into the cosine. So that shifts that to the minus 10. And then, let's see, this piece up here, though, then the minus 40 is going to be wrong. So 40 minus 90, 130. Yeah. I think that's where it goes. Does that seem right? It's the 20 minus 60 minus 90, right? Yeah.
Minus.
Yeah, but it's just the subtraction of the two, right? Yeah. And it's the 20 minus the 60, but then this has the extra minus the 90. So I think that's right. 130. So the cosine, I'm wanting to think about minus 130 doesn't.
Minus. It's not minus 30. The 60 minus 90 is negative 30, right? Yes.
60 minus 90 is negative 30.
We're subtracting that.
Right? Okay.
20, right?
And then 20, but so 20 minus 30, you're right, yeah, okay, so 50, okay, yeah, so this was not making sense to this number because it's a minus Cosine of minus 130 is a negative number, right? So that should have been a negative, but so yeah, okay, so you're right. Right, because this minus sign is the overall. I just subtracted 90. Sorry. You're right. Okay. So again, average power, the cosine of 50, that's positive, right? And so we're getting a positive average power.
What was the numbers you used to get 50 again?
Well, this phase shift of I, when I put this into cosine, from a sine into the cosine, I subtract 90 from this, which is what Mickey pointed out. So when I subtract 90 from that, I have negative 30. That's actually the theta I should use, negative 30.
Okay.
Right. And so then theta V minus theta I is 20 minus negative 30. So which gives me the 50. Yeah, so I forgot, I didn't notice the sign here, and so I should have made that phase shift right there. Okay. But we can also do this when we're talking about a phasor, right? Because if I have a phasor, I can put this into a cosine form. Okay. So we're going to deal with impedances and power and impedances in a few different ways. But for now, let's just look at this and get back to this form that I was just looking at. The instantaneous power is, little v times little I. There will be some other ways where we'll do this directly, but I just want to show you that we can get to the average power using the method we just saw, because if I know I can calculate v from the impedance, right? So the voltage, phasor form of the voltage, is just I times Z. All right? And so the voltage in this one, 10 times 20, which gives me a 200. And then phase adds, right? So 30, that's an angle of 8 degrees. So now I have the voltage, and now I can put this into standard time domain format. Right? I can put the current into time domain format, but I don't know omega in this case, so it wouldn't really matter. I can't put this into time domain because I don't know omega, but I'm not asked to find the instantaneous power. I'm only asked to find the average power. So to find the average power, what are the pieces I need to know? Well, I need to know Vm, Im, the phase angle of the voltage and the phase angle of the current. And I can look at these values and write those values down, right? So, Vm, the magnitude is just 200, and the phase is 8. For Im, the current has a magnitude of 10 and a phase of 30. So now I can find the average power, which we use big P for, typically. Right? Average power, 1/2 Vm, Im, right? Cosine theta V minus theta I. So 200 times 100, that's 1,000. Sorry, 2,000 divided times 1/2 is 1,000. Times the cosine of 8 minus 30. Did I do those right? Okay, yeah, that's all right, I guess. But so in this case, we're talking about the impedance, right? And so in an impedance, we can only dissipate power. So in this case, even this, so we should have cosine of negative 22 degrees. And so let me see here. I think I can I'll just double check our number, but I think that's correct. .927, yep. So this gives us 927. And yeah, the cosine of minus 22 is still positive, right? And so we can double check that this is correct. 927 watts. This is in an impedance. I have a positive power, which is what's dissipated inside of an impedance, right? So I'm dissipating, on average, 927 watts of power. Average power uses the unit watts. So does instantaneous power, because that gives us a representation of the true power moving through the system. As we move into these other topics, we're going to introduce a few different measures of power. Okay.